Hi there. My name is Neil Marya. On behalf of my co-authors, I'd like to thank the GIE editorial board, as well as you, the viewer, for your interest in our article entitled Application of Artificial Intelligence Using a Novel EUS Convolutional Neural Network Model to Identify and Distinguish Benign from Malignant Hepatic Masses. The identification and classification of focal liver lesions, or FLLs, are a critical factor for managing and optimizing care for patients, especially those with underlying cancer. For patients with cancer, 17 to 30% of those patients on cross-sectional imaging will be found to have an FLL. Now, of the FLLs that are identified in cancer patients, 11 to 37% of the FLLs that are deemed indeterminate based on radiologic criteria will eventually be found to be malignant. This is obviously very important because if a patient has a malignant mass in the liver that is a distant metastasis, this will often preclude those patients from being able to undergo a curative resection. Thus, being able to identify and classify FLLs correctly as being benign or malignant is key in providing efficient, optimal care for patients. Now, cross-sectional imaging such as CT or MRI is considered standard of care for the evaluation of FLLs. But certainly, endoscopic ultrasound provides us with a unique opportunity to evaluate FLLs. If a patient, for example, has a suspected pancreatic ductal adenocarcinoma, and we perform an upper endoscopic ultrasound to evaluate that, during our exam, we will be able to evaluate the liver, usually the left lobe of the liver and sometimes part of the right lobe of the liver. And during EUS, when we see these lesions, it's critical that we're able to help identify them and classify them correctly as being benign or malignant so that we can appropriately stage these patients. Our group previously has tried to see what we could do to optimize our ability to classify FLLs that we see on EUS. In 2015, we published an article where we got a group of experts together to come up with consensus criteria that could help endosonographers distinguish benign from malignant hepatic masses that are seen on EUS. In doing so, we identified that the criteria that we had developed was about 82% sensitive and 80% specific for the ability to correctly distinguish lesions as being benign or malignant. Now, we want to do more work in this arena to try and improve our ability on EUS to properly identify and classify FLLs. So how do we do that in this study? Our group has become very interested in the application of artificial intelligence and specifically using EUS as a platform. Now, artificial intelligence has become a big area of study in medicine, but specifically within gastroenterology. We're all familiar with the great work that has been done for colonoscopy and the ability to identify and classify colon polyps, but little has been done using EUS as a platform. And of the studies that have been done on that use EUS as a platform, most of that work has been done involving the pancreas, but very little has been done with the liver. So we were very interested in this. Our hypothesis was that we would be able to develop a convolutional neural network model, or a CNN model, that could evaluate EUS images of the liver, and we could use this convolutional neural network model to not just classify lesions, but to actually the first step to autonomously identify FLLs from an EUS image. Then we were interested in using the CNN model to take the next step in classifying the FLL as being benign or malignant. So how did we do this? What we did is we first identified 256 patients from a prospective EUS database that had examinations of the liver with diagnoses of benign FLLs, malignant FLLs, and diffusely benign livers. What we then did is we took out all the images and videos from those cases, from those 256 patients, and we randomized the patients to be being put into the training of the CNN model, to the validation of the CNN model, and then finally to the test model. So patients that were put into our test model were never involved in the training or initial validation of our CNN model. The next step was to first try and train the model so that it would be able to autonomously identify focal liver lesions. Now, this is one of the more unique features of our study, as we did not use expert-driven attention mechanisms to do that. We instead use occlusion block analysis to demonstrate that our CNN model was able to, on its own, accurately identify focal liver lesions. And in our results, we demonstrated that when we were evaluating video data from our database, the CNN model was 92% accurate in being able to identify a focal liver lesion. The second step of our study was that we wanted to see how well can the CNN model actually distinguish an FLL as being benign or malignant. Now again, optimal performance of our CNN model was found to be when we allowed it to evaluate video data, when it was actually looking at just the video data. And in doing so, the model was 100% sensitive and about 80% specific. So superior to what we have reported previously with expert-derived criteria. Now, while this is all very exciting, there are certainly some limitations with our work. First, we did not do a comparison of EUS to cross-sectional imaging such as CT or MRI, which is currently the standard of care. We know that EUS is quite good in comparison to cross-sectional imaging when we're evaluating sub-centimeter FLLs, but certainly this is an area that we'll have to look at in the future, is comparing our CNN model to cross-sectional imaging. Another limitation is that, as I mentioned earlier, EUS, typically we're able to see the left lobe of the liver quite well. The right lobe of the liver, we don't get a complete view. So certainly that's a limitation of the model, is that we're not completely evaluating the entire liver. Finally, our use of occlusion block analysis, while unique, is still in its development. So there's a lot that needs to be done in this arena. We need to see if we can make different types of analyses using occlusion block analysis and potentially use smaller blocks to allow us to compare the findings of the occlusion block analysis to the very small details that we appreciate as humans that we reported in our expert-derived criteria paper that I had mentioned previously. So I really appreciate your attention. I hope you enjoy our article, and thank you again for your attention. Thank you.